Our next technique is also a form of substitution, except it's a special form of substitution called trigonometric substitution. So this is called trigonometric substitution, or Trig Sub for short. So we could call this Trig Sub. So essentially what we're doing is we're using trigonometric functions in a substitution. So instead of just substituting, for example, u is equal to some function of x, we're actually relating x and a new variable theta via trigonometric relations. Now why would you do this? So this becomes handy when we have integrals like the integral of the square root of a squared plus x squared, or the integral of a squared minus x squared, or the integral of the square root of x squared minus a squared. And then many other integrals that will involve one of these three different quantities: square root of a squared plus x squared, square root of a squared minus x squared, or the square root of x squared minus a squared. So in each of these three cases, it reminds us of a right triangle because it reminds us of Pythagorean's theorem. So the whole idea is to construct a right triangle and use that right triangle to do a substitution. So instead of having one of these unwieldy square roots of something squared minus something else squared, which we cannot, as of now, integrate, we replace it with trig functions, which we are able to integrate. So basically in this lecture, I'm just going to look at these three basic forms and indicate which right triangle we're going to use to do this substitution. And then in our next lecture, we'll see some actual examples of this technique in action. So the basic three are square root of a squared minus x squared, square root of a squared plus x squared, and the square root of x squared minus a squared. So one of these three will be somehow involved with our triangle or with our integral. So what we're going to do is we're going to construct a right triangle like this. And for each of these cases, we're going to relate the variables to this expression. So let's consider the first case. So let's say we have an integral that somehow involves the square root of a squared minus x squared. It could be the integral of a squared minus x squared by itself. It could be the integral of the reciprocal of this. It could be the integral of x divided by this, and so forth. Now a squared minus x squared reminds us of a right triangle with hypotenuse equal to a. Because if the hypotenuse is a, then one of these side lengths will have the length square root of a squared minus x squared. So let's make the bottom leg equal to the square root of a squared minus x squared, and the opposite leg x. And we'll define an angle theta right in there. So basically we have a right triangle where one of the legs of the triangle is equal to the square root of a squared minus x squared. Now if we go to our three basic trigonometric relations, so sine of theta is equal to opposite over hypotenuse. So that's equal to x over a. Cosine of theta is equal to adjacent over hypotenuse. So that's the square root of a squared minus x squared over a. And tangent of theta will equal x over square root of a squared minus x squared. So this is opposite over adjacent. So these are our three main trig relationships. And these are basically the key to performing the substitution. Now the substitution itself is defined by the relationship that involves just x by itself. So in this case it's going to be x over a is equal to sine of theta. So basically we're doing a substitution with x is equal to a sine of theta. And then dx will equal a cosine of theta d theta. So you always take that simplest relationship, the one that only involves an x and does not involve any roots, and you differentiate that, or you take the differential of that to find dx in terms of d theta. So when you have an integral of square root of a squared minus x squared, the dx will be replaced with a cosine of theta d theta. And then you use these three relationships to convert from your functions of x to your functions of theta. And the idea is you convert everything to a function of theta and then integrate relative to theta. And then once you have your antiderivative in terms of theta, you use these three relationships again to go back and re-express your answer in terms of x. So for a squared minus x squared, this is the right triangle we want to use. So right now we're just going through and identifying our main right triangles. Move that up a little bit. So this was the first case. For the second one, okay, so for the second one, we're going to do the same song and dance again. So again, let's just draw a generic right triangle like this. And then we have our angle theta in there. Now in this case, we have the square root of a squared plus x squared. Okay, well that looks like the hypotenuse. So we make the square root of a squared plus x squared. That looks like the hypotenuse of a right triangle with legs x and a. So let's put x up there and a down there. Now you'll notice that there's not a unique way of placing x and a. Just like in the first case, there was not a unique position for x in the square root of a squared minus x squared. In other words, I could have put the x down here as the adjacent and the square root over here as the opposite and would have still had a substitution. Likewise, down here I could have put x as the adjacent and a as the opposite. However, the way that I'm doing these are the preferred ways of doing this. So when you do it this way, you end up more with tangent functions and secant functions that are relevant instead of cotangents and cosecants. So, you know, when you're deciding which leg to put where, put the x as the opposite and the a as the adjacent whenever possible. So for this one, this is the way you would set up the triangle. And then, of course, sine of theta will equal x over the square root of a squared plus x squared. Cosine of theta is adjacent over the square root of a squared plus x squared. And then tangent of theta is equal to x over a. So it's this third relationship that we'll use to find the differential. So from this, we get dx is equal to secant squared theta d theta. Well, we need an a in there. A times secant squared theta d theta, because the derivative of tangent is secant squared. So remember, you always write down all three relations, sine, cosine, tangent, and then pick the one that only involves an x and does not involve a square root. And then for the one that only involves an x, differentiate that to get your differential. And these are the three relationships that we'll use to transform our integrand into a function purely of theta. And then we'll use these functions or these relationships again to transform the antiderivative, which is initially expressed in terms of theta, back to an expression in terms of x. So our final right triangle, so case 3, let's call this case 1, case 2, and finally case 3. So this would be integrals involving the square root of x squared minus a squared. Okay, so again, we start off with just a right triangle. Oh, I actually drew that freeform. Oh, no, I didn't. Oh, I didn't know you can have. Okay. So we have this triangle like this, and now square root of x squared minus a squared looks like a right triangle with a hypotenuse of length x. So let's put x as the hypotenuse, a will be one of the legs, and the square root of x squared minus a squared will be the other leg. Now, there are three trigonometric relations. Sine of theta will be the square root of x squared minus a squared over x. Cosine of theta will equal a over x, and tangent of theta will equal the square root of x squared minus a squared over a. So the relationship we use to find our differentials is the second one. So here we can write x is equal to, so cosine is a over x, so x is equal to a secant theta. So I cross multiply to get x as a function of theta. So therefore in this case, dx is equal to a secant theta tangent theta d theta. Because remember, the derivative of secant theta is secant theta tangent theta. And you can do that just, it's 1 over cosine. Secant is 1 over cosine theta. So that's cosine theta raised to the minus 1. So the derivative is going to be minus 1 divided by cosine of theta to the minus 2, and then times the derivative of the inside, which is negative sine of theta. So sine over cosine is tangent, so we get tangent times 1 over cosine, so secant theta tangent theta. So those are the relationships that will be used for case 3. These 3 relationships down here. So basically these are our 3 right triangles. So given one of these types of square roots, either a squared minus x squared, a squared plus x squared minus a squared, it's simple to identify the hypotenuse. In this case, it's a squared plus x squared, so that's going to be the hypotenuse. In this case, a squared minus x squared, so since x squared is being subtracted from a squared, a belongs in the hypotenuse. In this case, since a is being subtracted from x, x goes to the hypotenuse. So first identify the hypotenuse, and then from the other 2 sides, if you have an x left over, it always goes as the opposite. If you have an a left over, it always goes as the adjacent. If you have both an x and an a, x is opposite, a is an adjacent. So if you haven't used either a or x as the hypotenuse, put x as the opposite and then put a as the adjacent. And that's how you construct your 3 right triangles, and then do the substitution, integrate now a function of theta. You have an antiderivative in terms of theta, and then use those 3 trigonometric relations to go back and re-express in terms of x. So our next lecture, we'll see some actual examples of how to actually employ this technique and solve some of these sorts of problems.